Yeah, sorry, I have to pick up the pace sheet.
Okay, if everyone could grab a seat, we're going to get started again very shortly with Christopher Beckham, who is working with one of the giants of deep learning, Yoshua Bengio, and he's going to tell us a little bit about generative adversarial networks that a couple of you asked me, how can you generate more data? Well, pay attention here.
Thanks, Andrew. I was going to see if the mics you guys hear me good? Everything's good? Cool. Okay, so generative adversarial networks. So this is something that I've been doing a lot of research in lately. I'm passionate about. It's the results are amazing. Like, there are so many cool things that you can do with it, and I'm happy to teach you about it today. Really just the tip of the iceberg, because there's so many things you can talk about with regards to this. So without further ado. So here's this awesome quote from Richard Feynman: "What I cannot create, I do not understand." And I feel like this really summarizes generative adversarial networks, because, I mean, what GANs do is that basically they learn to generate data. So if you have a training set, which is, you have a collection of data, it's going to learn how to generate that, or learn how to generate things that could plausibly come from your training set. And so, the question is, I mean, why is that useful? Why is it useful, learning how to generate the data? You could, this quote from Richard Feynman is that, well, what this is really saying is that if you know how to create the data, then surely you actually know the useful things about it, right? I mean, an example is like, forging money, right? If you can create counterfeit money that's indistinguishable from real money, then surely you know something about, right, how to make really good-looking money that can fool people. I mean, that's useful, right? Very useful if you're a counterfeiter. So I'm going to give an example here, actually, a similar analogy to the counterfeit money thing, but, you have the Mona Lisa right here. And so you have this detective guy here, and he's called the discriminator. I forgot what this guy's called, but he's from a cartoon. Yeah, thank you. And so he's got this magnifying glass, and he's going to look at the painting and say, is it real or is it fake? And so he's called the discriminator. And you have this mischievous dude here called the generator. He's the forger, and this is, I remember his name, this is Taz the Tasmanian Devil. And basically, he's going to try to forge this painting. He's going to try to generate a fake and fool this discriminator. But obviously, at the start, he does a poor job, because it's like a very blurry, sort of non-faithful kind of reconstruction. But basically, the generator and the discriminator, they play this adversarial game where they're both trying to one-up each other and beat the other, that over time, he learns how to generate something that is a lot closer to this Mona Lisa. Right. So this is really the high-level overview, the intuition behind GANs, generative adversarial networks. So I'm just going to formalize it a bit more in 4 bullet points. What are generative adversarial networks? Well, basically, they're a class of algorithms used in unsupervised learning, in which the goal is, in an implicit sense, to basically learn the data distribution. And so what do I mean by that? So, in deep learning and statistics, often we talk about this thing, the data distribution. But really it doesn't exist. It's not some mathematical function we can sample from. Like the data distribution is the universe in which we exist in, right? It's not like some function that we can run, but we have samples from this data distribution. That's called our training set, right? So our training set is like sampling from this distribution, if you want to think about it in a statistical manner. And so what GANs do is that they try to sort of implicitly learn or learn from the empirical sample of your data distribution. So this is done through 2 adversaries, the generator and discriminator, or in our money analogy, basically the detective and the forger. And basically they compute against each other in the zero-sum kind of framework. And so they compete against each other until a Nash equilibrium is reached. And so by that I mean basically they're at an equilibrium where if one tries to change its strategy, it actually does worse. So basically one is no better than the other, essentially. And so theoretically, I'm not going to go into this, but I think it's really useful to mention is that basically if you go into the math, GANs are basically doing this thing called divergence minimization. And so if you have 2 probability distributions, you can define a distance between the 2 distributions. So you have your real distribution, your fake distribution. And essentially, the discriminator is trying to force the distance between these distributions to be far apart, and the generator is trying to make that distance very small. And so it's actually very mathematically grounded, although we still have a lot to understand about it, and I just think it's worth mentioning. So here's how the generator works, essentially. So really, in order for you to generate samples, you have to start off in this space here. So this is called a prior distribution. And so in this case, it's a simple 2D uniform distribution. And in order to generate a sample, we need a sample from this distribution. And so you can think about sampling from the prior distribution as basically you're coming up with some noise. You want to generate some noise that you can use to produce a sample. And so we're going to randomly sample in this unit rectangle, some Z, and basically we're going to feed it through our generator, G of Z, and we're basically going to get a point here, which is X tilde. So this is a mapping from the space of a prior distribution, which is a really simple distribution that we know and we have in closed form, to basically a much more complicated, higher dimensional distribution, which is the space of the data. And so this is what the generator is doing, basically. It's mapping from noise to data. So I think I mentioned it here. So yeah, so you can summarize the slide by saying we can model arbitrary distributions by sampling from a simple distribution called a prior, and then mapping the sample through a sufficiently powerful function called a generator. And so what is this sufficiently powerful function? It's the deep network. So here's another way to look at it. This is a more, I guess, concrete version of the previous diagram. We have some random noise here that we sampled. This is our noise source. So mathematically, you can write that Z is a sample from the distribution P of Z. And so P of Z is our two-dimensional uniform distribution. We're going to feed it through a generator. And so X tilde, which is our fake sample, is G of Z. And in this case, this is actually the opposite of a convolutional neural network. I mean, we haven't talked about it at all, but basically it's the opposite of that. And so a convolution has a contracting pathway. It tries to reduce spatial dimension. And the transpose convolution basically does the opposite. And so in this case, we go from noise to an image. So just to recap, the generator takes noise, a source of stochasticity, and basically transforms it into something that could plausibly come from the real data. So basically, I'm going to summarize it here. So basically, you have a Z, which you sample from P of Z. That's the noise. And I've changed the picture. It's not a Tasmanian devil now. It's a box. It's a box of a crank. So it's like you feed it noise, you turn the crank, and you get a fake image from that. And so, so that's your set of fake images. But you also have the real images, which is sampled from your training set. And so just to give some illustration, so this noise source here is a Gaussian distribution, and you have your fake samples and you have your real samples, and basically these get put together, and basically they go to the discriminator, and then he's going to basically output a probability saying, what percentage of these are real and what percentage of these are fake, right? So this is one half of the GAN algorithm, right? So the other half is how exactly does the generator try to fool the discriminator? Well, what I'm going to do is that I'm going to give a high-level overview of the GAN algorithm, and then I'm going to do another diagram that's going to piece the whole thing together. So let D denote the discriminator with D of X outputting a probability. So this denotes how the discriminator is saying it's predicting how real it thinks this image is. And so D wants to do the following. For the real X, for the real data, it wants to update its parameters through backpropagation such that it wants to minimize this equation. And so this this is just a distance function. And so in this case, you can think of it as like a squared error loss function. So you want to minimize the distance between the squared error between D of X and 1, where 1 denotes 100% real. For G of Z, so G of Z is the X tilde. This is the fake sample. It wants to update its parameters so as to minimize the loss between D applied to G of Z and 0. And so it wants to output 1 for real and 0 for fake. G wants to do the following. G wants to do the opposite of this, actually. So G wants to update its parameters so as to minimize the opposite of this. So it wants to minimize the squared error between D applied to G of Z and 1, right? And so to put that in a diagram, so I'm just saying here L is the squared error. so what we're doing here is that we have our fake samples from the generator, and then we're going to feed it through the discriminator, and it's going to basically minimize the squared error. So the squared error between the fake samples and 0, which is fake. And then it's going to do back propagation and update its parameters. And so for the real samples, it's going to do the same thing, but now it's going to compute the distance between this and 1, so that's real, and it's going to do back propagation, and it's going to back propagate the gradients. And so the generator here, so these are the same, I'm just copying the picture over, but now it has these generated samples, and we're going to feed it through the discriminator, and it's going to minimize the opposite of this equation here, so we just have a 1 here. And what it's going to do, which might be a bit of a mind bender at first, it's going to backprop, but it's going to back propagate through the discriminator, right through it. So basically, it's going to try to fool this guy, but it's only going to update its own parameters, right, when it does the back propagation. And so this is essentially one iteration of training again. You do this for like as many iterations as you want, and that's really the algorithm. So. Yeah, I mentioned this at the start of the talk, right? What is the use of learning to generate data, right? Because it's quite a different paradigm to what we did earlier with classification or other things like clustering. It's a completely different way to think about how to do machine learning. Well, like I said, maybe it's the case that you actually want to generate or augment data, right? So here is actually the style transfer thing that you might remember Andrew had this with the brain painting. So maybe you want to do something that's related to generating data, where maybe you take the picture of this cute little Shiba and this painting, and then you do like a style transfer thing. So you can use GANs to do style transfer. Here's something that maybe you'll see in Photoshop in a couple of years in painting, right? If I obscure a region of the image, use the GAN to basically infill. Right? So this actually came out really recently, actually this year. So maybe you want to fill in missing data, right? And I think there are papers doing this in medical imaging as well, so maybe that's interesting to follow up on. So you can also do things like maybe change the attributes of a person, change their hair, color, their gender, and so forth. And so maybe you could plausibly use this as data augmentation, right, to generate more data for your deep neural network, and that's a valid thing to do. And so here's really that was my first answer to the question. The second answer, which I feel like is the key thing, if there's anything you should take away from this talk, it's this, is learning to generate data may actually help with downstream tasks. So again, this quote from Feynman, what I cannot create, I do not understand. If you know how to generate the data, then surely you've learned interesting things about it, right? So you guys are probably all familiar with Bayes' rule, P of y given x. So say, for example, y is the label you're trying to predict, and you condition on x, can be written in this form here, which is the joint of x and y divided by p of x. Well, GANs are implicitly learning p of x, right? So this is why I said it's a class of unsupervised learning algorithms. And so, just looking at Bayes' rule, right, if you can improve your estimate of p of x, then you implicitly improve your estimate of p of y given x. And so through Bayes' rule, we can see there's a connection between the two. And so here's a concrete example, right? If you're doing supervised learning where you only have labeled data, you're trying to draw a decision boundary between the black and the white dots. So these are the two classes. But what if you have unlabeled data here, which is the gray ones here, right? Then this decision boundary is not actually the right one, right? So if you do purely supervised learning, guess what happens to this data? You don't actually use it, because your algorithm doesn't support it. But if you use GANs, for example, you can actually, or other unsupervised learning algorithms too, you can actually incorporate this data, and this data is actually going to help sort of mold this decision boundary. And so, I mean, you think about medical imaging, for example, right? I mean, it's very expensive to label, CT images and so forth. So, I mean, this is something that we should all be excited about. So I'm going to give another example here. I realize we haven't gone into autoencoders, which are another thing you can do in deep learning. But autoencoder is basically a neural network where you encode your input, you decode it, and you get a reconstruction. And basically, it's a neural network that learns to reconstruct its input. And so you basically minimize this loss function. It's the Euclidean distance between x and the reconstruction. And so you might ask, well, what's the purpose of doing that? It sounds pointless. Well, the idea is that in the middle of the network, you are basically compressing, you want this hidden layer to be very small. And so what happens is that this network is forced to learn the latent variables that really characterize the data. And so basically I say here it's cooler than PCA. The reason why I say this is because you can actually show mathematically that a very simple autoencoder actually learns something very similar to PCA. And so this is basically like a deep learning version of PCA. Yeah. And so we can actually use generative adversarial networks to improve this. And so, I mean, in a nutshell, Euclidean distance, which is this loss function here, it's basically a terrible perceptual similarity metric. And so you could have two images that look very similar, but maybe you add some noise to one of them, and when you compute the distance between them, the Euclidean distance, it's really big. And so, I mean, it's an okay loss function to use, but it's not really a good similarity metric in terms of our perception. It turns out that you could keep this loss function, but then add a GAN, add a discriminator, and now the discriminator is going to detect whether it's looking at a fake, a reconstruction, or if it's looking at the real deal. And so if you do this, you'll see. So this is from a paper in 2016. If you do just an autoencoder, you get like these blurry-looking outputs. But if you combine the autoencoder and the GAN, you get these crisper-looking outputs, right? And so this can actually help to make your reconstructions look better as well. The last thing I want to talk about is actually the manifold hypothesis. And so just imagine for a second you consider all the possible 128 by 128 RGB images, right? Well, each pixel, if you assume that each pixel can take on 256 values, so that's a byte, sorry, a bit. No, sorry, 8 bits. It's 8 bits a byte. So the number of possible images that you could generate is 128 by 128 by 3 channels RGB, and 255. So that's 12.5 million possible images that you could enumerate. But obviously, I mean, this diagram kind of illustrates it. Most of the time when you randomly generate a 128 by 128 image, it's not going to look anything like a real image, right? So I mean, just because you have 12.5 million possible images does not mean all of those 12.5 million look real. And so this is the manifold hypothesis, is that the real data lies on this thing called a low-dimensional manifold in high-dimensional space. And so you have the super high-dimensional space, which is like, you can't see it, it's many dimensions, but only a small subspace contains the plausible images. And so this is really what deep neural networks actually try to do. They try to recover, they try to learn the data manifold. And so I'm mentioning this because it turns out that if you imagine this square to be the prior distribution, that say, for example, the 2D square that we saw earlier, basically, the prior, in a sense, is a representation of this data manifold. So what do I mean by that? If this is your Z, the space of your prior distribution, you may have an image here, Z1, which corresponds to a dog when you run it through the generator. And on the other side, you may have a picture of a train, say Z2, when you run it through the generator. And so what happens if you interpolate between these two images in Z space? Well, you get something that looks like this, right? So basically what I'm trying to say is that when you train a GAN and you look at the Z space, you actually get something that's very semantically meaningful, right? You can find this online with, say, faces, for example. You can actually take two people's faces and basically average their Z vectors, and then when you run it through the generator, you actually get a hybrid. It's amazing. And so this is really called walking the manifold, right? We've actually learned the manifold, and when you walk down the manifold, you actually get plausible-looking images, and if you walk off the manifold, you get just garbage, right? So that's precisely what I mean, what I'm trying to convey here. So yeah, I'm not done yet. Hold on. I have an animation to show actually of. So here is actually, hopefully I'm good for time. Here is actually, this is basically 500 epochs of training again, basically. And so every epoch, it's basically trying to fool the discriminator here. And so you can actually see over time what's happening is that it's very, I know it's flickering and it's very hard to follow, but if you just look at one cell, you can actually see this particular Z value evolving over time, basically, right? So I find these pretty pretty fun to watch. I don't know about you guys, but this is really a time lapse of training a generative adversarial network. And I think that really concludes my... thank you. Sorry?
What was Z?
So Z is basically sorry, I can't go back to the slides here, but basically so initially when you're training a GAN, you need, in order to randomly generate the image, you need to sample from a noise source basically. And so this noise source, that vector that you sample from the noise distribution is basically Z. So in the diagrams earlier in the presentation, I had this rectangle, and so that's basically a two-dimensional uniform distribution, and so Z would be a two-dimensional vector in that rectangle. Yeah.
And how did you move through the vector?
Yeah. So basically, so the generator is your deep neural network, and you're going to feed it Z, and then it's going to output X basically.
Okay.
Right.
This is the X that you are printing.
Yeah. Yeah. And so basically the generator over the course of training is going to try to output an X that could fool you basically. It's like this could plausibly come from your training set, but it doesn't. It was actually just generated from nothing essentially. Yeah.
How did you get a brain from a cat? So Z was a cat.
Well, Z, I mean, so basically in sorry, I don't know if can you? Yeah, sorry, because I can't see the doc. So oh, here it is. I think it's that one right there.
That one?
No, that one right there. Yeah, that one.
Yeah.
Yeah. Thank you. So so let me. Yeah. So I mean, this is really just for the sake of example, but I mean, so you can imagine that I'm sampling Z1. I don't know what it is, right? But I'm just going to sample it. But you know, maybe in this example, when I feed Z1 through the generator, it outputs the picture of the dog, right? And Z2, so I'm sampling Z2, and it's somewhere else in the distribution. Maybe it's somewhere else in the cube, and then maybe when I feed Z2 through it, I get a train, right? But what's interesting is that if I interpolate between, so maybe if I take half of Z1 plus half of Z2, I'm going to get something that's in the middle here. And so I'm going to get like the Z average, and I'm going to feed this through the generator, and I'm going to get this like, maybe this is I don't know, these are you can kind of see the dog here, right? So yeah, something like that. So someone had a question in the back, did you? Yeah?
Yeah, about this manifold hypothesis.
Do you want to use this?
Yeah.
Just so people can hear.
Sure.
Thanks.
So, is it okay?
Cool.
So, I think in image compression relies on this basically the fact that real images are, for example, dominated by low frequencies.
Yeah.
And that's why the frequency domain is, in general, much more informative of an image, and the information of the image is much more compressed.
Yeah.
In the low frequencies.
Yeah.
And also for example, the discrete cosine transform basis, which is used to compress these images. It looks a lot like some of these learned patterns that we've seen from the convolutional neural network. Only it gives you it right away, because it's basically the basis used to represent the image. So I'm surprised. Is this used at all in neural networks for images?
You mean is GANs used to help train?
No, I mean is the frequency domain?
I'm actually not sure, because it's not really my particular domain. But yeah, I'm not sure. Sorry, actually.
You certainly see that like wavelets appear.
Yeah.
So I think, but it learns the wavelet transformation.
But
Right?
doesn't
So I
that?
guess you could jump ahead and like do a wavelet transformation and feed the wavelets directly, right? And I don't know. Like,
No, actually, it doesn't work like that. It needs raw data.
okay, it still needs wavelet. Okay.
It works best when you give raw data.
Okay.
So I've seen some interesting work unrelated to image compression, but for training neural networks based on real neurons, where they're trained using backdrop prop in the frequency domain to produce spike trains in the time domain, and then
compare it against real neuronal recordings. But I don't know. I think we're at the beginning of this kind of thing.
So Chris, I have a practical question then.
Yeah.
So you could take GANs and generate anterior, posterior flipped brains and then feed them to Anisha to see if she could do.
Yes, you
her-
can. You can.
Okay.
You can definitely do. Like again, when you're generating data, you have to be careful. But yes, it's actually one of the big things you can do with GANs. You can use them for semi-supervised learning, so you can generate more data to basically, essentially.
And
yes.
is there any evidence that there has been any like bias detected in GANs?
Well,
versus,
actually, yes. I
natural
would like
data?
to. I would like to actually mention one in domain translation, which was the horses and zebras, for example. So actually, a colleague of mine, did this paper saying that when you use GANs to translate from CT to FLAIR or T1 or whatever, because it's like it's with a very, very low level of supervision. What can happen is that certain biases in that data can basically affect. So what I mean is, like, if you're translating between, say, T1 and FLAIR, for example, what if the T1s have more sort of sickness in them than the FLAIR? And so what happens when you translate from FLAIR to T1, it basically generates sickness. And so there was a talk at NIPS last year by Kate Crawford, which is like biases and algorithms. This is actually like a big deal in AI. Your algorithms will become biased if the data is biased, and if it's very easy for biases to kind of turn up and kind of mess everything up. But assuming your data is clean, why not, right? Try it out and see what happens.
That was it. Yes.
Cool.
I think that's it for the questions. So we'll go ahead and move on to Pim. We can get started. Thank you guys for the great questions.